My name is KKjerrumgaard. I'm a Apache Pulsar committer. That means in the Apache open source world, not only can I contribute code, but I can also approve patches from other people and get them merged into the code base. So I'm also the author of Pulsar in Action, which is available for free download on the StreamNative website. If you go to our resources section, ebooks, it's there available for download, the entire book. This particular training around 3 different ways to implement SQL using Apache Pulsar. What we're going to cover today as far as an agenda is we'll cover 3 different paths of SQL within Apache Pulsar. The first is the standard, what's called Pulsar SQL. Traditionally, that was the first capability that came out. That's based on the Trino and the Presto plugins. And we'll talk about those capabilities. That's all directly native, to Pulsar, comes as part of the Pulsar package. The second is leveraging the Flink connector using and Flink SQL to read the data directly from Pulsar topics and execute queries using the Flink SQL engine. We used to offer Flink SQL and Flink as an offering with StreamNative, but no longer do that. So if there's any references to that in this documentation, just know that they'd have to stand up their own Flink cluster, maybe with a partner like Ververica or Immerock or whomever we decide to go with as far as a Flink partner. They would handle the Flink part of this, but we could still access Pulsar data using SQL queries this way. And then last but not least is the new interesting, what we call right now, the StreamNative filtering and routing services. I'm sure it's going to be changed in marketing to be something a little more interesting, but this is basically a broker side filtering service that's provided by Pulsar that uses a SQL interface to dynamically filter messages before they're sent over to the consumer. So you can do things like content-based routing before you send all the data to the consumers. And then last but not least, we'll talk about roadmap and next steps as well. But just so we have a basic understanding of what we're talking about. What we're trying to cover in this course is obviously how to query data using Pulsar SQL, be able to write how to write continuous queries using Flink SQL, because Pulsar SQL does not support continuous queries. They are point-in-time queries. They run data against static segments, and that's what you get. They do not update. So it's a one-time shot, get the results. Whereas Flink, it's a continuous, or it supports continuous. You can also do single shot queries with SQL, just to be clear. And then we'll talk a little bit again about the new StreamNative's filtering and routing service and the SQL languages that's supported, and a little bit about how it's implemented using Pulsar Functions under the covers to implement this new capability, this broker side filtering as well. So let's start at the beginning with Pulsar SQL, right? We're going to talk about the Pulsar SQL architecture, how the data is accessed directly from Pulsar using the query engine Trino or Presto. Typically, we ask the developers or attendees to have completed our fundamentals and developers training and have some understanding of SQL. And then just talk about when's the best case to use this particular approach for Pulsar SQL. When consumers are asking, clients are asking which approach should we use, this will give you some guidelines about when to recommend this approach to them versus the Flink or the filtering and routing service. So what is Pulsar SQL? It's a way of using SQL to query data in Pulsar. It's just sometimes it's easier to use that way, right? You can store a lot of data inside Apache Pulsar, and sometimes it's easier to explore this data using SQL statements rather than low-level code. But oftentimes before to do this, you had to offload your data to another platform that supported a native SQL execution engine, right? That's typically was the offloading platform. You have this intermediate buffer, would be what Pulsar is. You'd have to, CDC, change data capture, or stream it in, doing updates, inserts into tables that supported SQL, and then you could run it there. This allows you to maintain the data inside Pulsar entirely and just query it with an external query engine. And this eliminates the need to duplicate that data, have that data skew between what you actually consumed inside Pulsar versus what you migrated over to this SQL query. And so you're querying the data in as near real time as possible. You have there is no skew between one data set and the next. Again, as I mentioned, Pulsar is used to store streams of event data, and that event data is structured. As we know in Pulsar, every topic has a schema definition that can be byte arrays, but in general, we want to have a more strongly typed schema that defines the fields, the types of those fields, so that we know what the data looks like inside each one of those. And the Presto Pulsar connector enables Presto to come in, Presto is a distributed query engine written, I believe, at Facebook that can come in and access that metadata, right? So it goes and it queries that metadata, says your table looks something like this. And then when you want to query against it, this Presto execution engine will figure out how to read those records and bring those back to you. And so the Presto interface is designed to query data from multiple data services as one, rather than a single system, right? Prior to Presto, you had a single database engine and you stored the data on that same SQL platform. And so you could only query from one particular system. The people at Facebook figured out, hey, you know, rather than move the data into the system, like I mentioned before in the previous, which is a bottleneck, let's just leave the data where it lies and figure out a way to query these separate resources. And so you can join a query with data from a Pulsar topic, from a traditional database, from an object store, and read all that data using this Presto query engine. And all you have to do is provide a connector that is able to get the metadata to identify what the tables are, and then be able to read your data in its native storage language, right? So this was a service definition interface that if you provide it and support it, Presto can just leverage that and go read the information directly off of Pulsar or whatever system you have and do that automatically, right? So this allows Presto then goes directly to the BookKeeper layer to read this information rather than having to route these requests back through the Pulsar brokers, which alleviates some pressure on those brokers as well. So it's a nice design structure. And it looks something like this. Let's just talk about it graphically, right? So Pulsar SQL is really the Trino query engine under the covers. And the Trino query engine basically plans and executes the entire execution path, right? So you can be querying Pulsar directly, or it can be a subtable, a subjoin in another query from another table as well. So these SQL queries down here is what this query coordinator decides who I'm going to query the data from as far as bookies are concerned. And it has a sequence of parallel SQL, what's called SQL workers, that can read these, execute these queries in parallel, filter out the records, and combine them back together to ultimately give you your results, right? So as I mentioned before, this completely bypasses the Pulsar serving layer on the brokers. We just go directly past it. You only have to get the metadata once. You go to the broker layer once to get the metadata for that schema. Once you have it, you can continuously read directly from these bookies. And this allows you, by going to these different bookies, by having different segments or the same segment across multiple, not only different bookies. So if you need to read segment 4, for example, you have your choice of bookies to read that from. But obviously, you're going to have a fan out query where you're going to read multiple segments across that same topic as well. So you can have full fan out IO bandwidth across all these bookies for much faster queries as well. So this is the architecture and how it's laid out inside Pulsar SQL. So adding some structure to that, the query coordinator receives the schema, goes back and gets the schema for the topic to create the table model. And then the query coordinator determines to spread out the load across all SQL workers so that they're evenly distributed, right? It's going to say, okay, I'm doing a filter on this, which segments are related to this topic, and then I can scan those topics or those segments that are associated with those topics in the bookies, and they can read and execute those results in parallel, and then again can funnel them back to the Trino query coordinator, which takes those results and merges them back together. It gives you a complete result set. So just some generic commentary on the syntax around writing this, right? So you have to start it using the Pulsar SQL command from inside a Pulsar, the standalone console. So you open up you have a shell, you start with Pulsar SQL, it brings it up the query, and then you can run it. Syntactically, you have to terminate all your queries with a semicolon here. If you're querying anything that's related to strings, use a single quote, not a double quote. And if you run a query with multiple lists, then the Pulsar SQL will show a list and you have to tabulate through it. So it'll generate a list of like 20 or 30, and you have to page down to go through that list and navigate through that list. They're all there, but they only show a subset of those lists. When you're finally done with all your SQL queries, you type Q to exit that session, and it'll just terminate that particular shell, that query shell that you're using to query Pulsar on that. Also note, so that's the exploratory way. You can do that very quickly, quick and dirty. The more natural way to do this for consumers is to run using the Presto or Trino's REST API. They have a public REST API. You can publish your queries there, and then the results are returned as JSON, and then you can store that JSON and do whatever you want. So it's a good way to, if you want to do some filtering, right? If you want to say, I want to take all this data, static data from a topic, or join this topic together and do, grab me only the records that have, for this particular field, have a certain value, and then dump that to another topic. This output is JSON as a way to do that, right? So you can run the REST API, get those results, return as JSON, and then rewrite them as new records inside another topic, and then it's there for filtering, right? So this is a way to do it after the fact as well. This is just the basic exploratory commands that are available with the Pulsar SQL. The show command, basically shows you all the different ways that data that's available. Again, so in Pulsar, the namespaces map to logical database schemas. Pulsar topics map to tables, the corresponding tables, and schemas. Pulsar schemas map to database definitions, right? So namespaces show all your tables. An individual table is a topic. And then again, as I mentioned before, you can get the schemas on a per topic basis. Note that you have to double quote all the tenant namespace, just because that backslash is interpreted as an escape character for the Trino and Presto interface. So this is the only place where you use double quotes when you're querying or interacting with the Pulsar Trino, the Pulsar SQL command line shell. This is where you have to double quote things because of that. It supports all your standard SQL syntax. So again, go to the Trino or Presto docs for more details about what the limitations are, but it basically supports all your different select commands, your where commands, limits, likes, ands, etc., counts, group bys, etc. All your different aggregates are supported as well. Order by, everything is really very, very broad supported set of SQL syntax. I'm not sure if it's 100%. But it's very close to 100% of standard SQL. So there are very few limitations on this. If we're recommending it for a customer to use, they're fairly confident they can use all the SQL syntax that they want to without any issues whatsoever. And although it's not shown here, joins are also supported by Trino, right? So these joins are also a standard thing as well. You can join to other Pulsar topics. You can join to non-Pulsar topics. Again, a relational database that you've configured Trino to access from, that's something you can join as well. So there's really no limitation on what you can do with the SQL queries. So as I mentioned before, to execute the query in the query coordinator, the Pulsar SQL needs to know the schema, and they're accessible from the broker and stored in BookKeeper. So again, that's why it has to interact with the broker. And when you configure the Pulsar SQL client, it has to have access to the broker, and this is why. But again, it only goes there once. It doesn't go there for all the additional queries. It goes there to get the metadata for a specific table. And it needs to know specifically the name of the column for filtering, the type of the column, so it can map it to the typing information, so it can do the comparisons if necessary, and whether it's nullable or not. So it needs that information as well. And that's the type of information that it gets. And again, if it's a schema supported, either an Avro or JSON record type, it'll be able to interpret that correctly and turn it into an appropriate table definition that Presto can then use to execute its queries. So Pulsar SQL is a useful tool for answering questions about data in your streams, such as basic analytics or searching for specific data. So some of the different use cases people use are, real-time analytics. You want to query data as soon as it's received by Pulsar, make it possible to run SQL queries that can incorporate the latest data for real-time dashboards and monitoring. You don't have to have this latency of I have to move it to another, SQL-backed database in order to run this query. So you minimize the latency of getting that data available for your SQL query engine. That's good for web analytics or mobile app analytics, where you generate usage and interaction data that can be queried to detect usage patterns, improve application response time, customize experience, and a lot more events in real time. You can also do event logging and analytics, so you can ingest different logs and from operational systems that's stored in the Pulsar. Then Pulsar SQL can query them to use to gather information to quickly detect, failures, bugs, query for errors, look for any sort of exceptions in these logs. So you can quickly identify these events in real time. You can also do an event replay. You can query back from the beginning, select star from, allows you to extract a series of events in the sequence they occurred using the SQL query. So again, if you want to give me all the events from this topic from point A to point B as far as time frame is concerned, you want to replay those events for whatever reason, you can use that using, the where clause and the timestamp to say the timestamp between here and here, for example. You can use this, to go back and identify, things that happened in the past. If something bad happened in the past, you had a lot of fraud transactions coming in all at once, you can go back and take that analytical data from that period of time and figure out what happened and do a postmortem and figure out what went on inside your data. But you have all that information there, and you can narrow down that particular window of time as well. Let's move on to the second option for SQL with Apache Pulsar. So this is Flink SQL. We're going to talk about how Flink SQL works and some of the use cases that are best suited for Flink SQL versus the Pulsar SQL. So let's take a step back and understand what Apache Flink is and how it fits or how it differentiates itself from Pulsar, right? So it is first and foremost a distributed computing engine, right? It's a massively scalable system. It supports high level of parallelism across the system. So you can run multiple tasks simultaneously to read data, similar to what the Presto query did with its SQL workers. Flink has a similar model of highly scalable, horizontally scalable system. It's designed to execute any sort of user code versus specifically SQL, which is the differentiator between it and Presto. But it also supports a native SQL interface. So you can type in a SQL query into your the Flink SQL engine, and it translates that into lower level tasks and data flow graphs as shown here. So at the bottom, you can sort of see here, I'm circling this little graph. It takes that SQL and maps it out to I have to select from table A and table B, filter out those data together, route it over to this particular join operation, and then at the end of that, out come your results, right? So it can turn that into an abstract syntax tree and then to an execution plan. And those execution plans are then mapped to individual tasks in Flink, and then they're executed in parallel, and they can exchange data directly between one another with networking connection and things like that. It has that all built in for that. And it also supports stateful processing, right? So it supports the concept of checkpointing, having a process up to this point in time. And if anything fails, it can move back to that safe checkpoint and reprocess the data. So it's more resilient than something like a Pulsar function, which is not stateful. It just processes the data once. Here with Flink, we do checkpoints along the way to make sure if anything gets out of sync, anything fails, because it's a massive distributed system, things can fail. So it uses the checkpoint coordination to make sure that everything, is in sync and processes as expected, right? So it's a great way of joining different streams together, for example. So Flink is a complementary technology to Pulsar. Obviously, it provides advanced streaming computing capabilities on top of Pulsar topic data. And it's a good alternative to things like case streams, for example. Similar things you would do with case streams with the Kafka before you use KOP. We would say for Pulsar, you just want to use Flink. Why rewrite a distributed processing engine? That's hard to do. Let's leverage Flink. Let's leverage Spark to do these types of things. And then Flink is just built in with the connectors to read this information, right? So data will always come into Pulsar there, and rather than just using Pulsar Functions or traditional client libraries to get this information, and you want to again use things like SQL interface, then Flink is a great tool for that. It plugs in directly and it can get that information directly using the Flink connector that was shown here. So this is what makes it possible, right? They're complementary technologies that run side by side. Again, this is where I was mentioning StreamNative Cloud used to offer Flink. We no longer do that. We just shrink this window over to say Flink is a partner technology at this point, but everything else remains the same. It's just a matter of ownership here in this particular slide. So how that is possible is the fact that there's a Pulsar Flink connector that allows Flink to read and write data directly to and from Pulsar topics. And this makes the Pulsar topic available for Flink SQL queries. This one's probably a little dated. This is a link to the 1.13. I think we're on 1.15 now is the latest one available for that. And so again, it allows you to leverage the Flink processing engine to read data from Pulsar, write it to Pulsar, and provides exactly what source semantics and at least once sync semantics are provided by default out of that. So again, we have both a source connector, so you can read it from Pulsar, and you can have a sync connector, so you can direct any results of your queries back into a Pulsar topic as well. Right, so these are just some details around how making this available, right? So for the Flink to access the data in Pulsar, the connector jar must be added to the Flink jobs class path. This is traditionally done by putting either in the Flink home library, which is their global class path library, and it would get included in all Flink jobs, whether they're using Pulsar or not. Or you can add it, pass it through in the command line here using this embedded jar command to pass in your different versions and pass it in. So it would be provided just for that individual job as well. So there's two different options there. And so this is just the semantics of getting that library available for your runtime environment. So Flink SQL is now, what is Flink SQL versus Flink, right? So we talked about Flink. It's a distributed processing engine. We have now a way of plugging it into and reading data from Pulsar, so that's great. But how do you have Flink execute SQL for you, right? So it is a completely interactive interface that allows you to query any sort of data, Pulsar just being one of it. And it's something like this. There's a SQL gateway that sits in front of your SQL commands, again, that you must authenticate through, but then you pass in your SQL syntax to this gateway, and it translates that again into an execution path plan. It figures out where it needs to go to read data from what. Does that based on the Pulsar catalog. So again, it has to have access to the topic names, the schema names, just like we did in the Pulsar SQL interface. It needs to understand where that data is and where it needs to read it, and then it's going to convert that information into tasks, as I mentioned before, and submit those to the Pulsar or from the Flink to the Flink session cluster. And that Flink will then take those tasks, execute that information. When it needs to read the data from Pulsar, it will use the Pulsar connectors, source connectors. If it wants to write the output to Pulsar, it'll use the Pulsar sync connector, and everything else is just directly executed inside the Flink query engine. And the metadata queries are done up here. So it's a complete separation between the two. There's three different layers here: the SQL gateway with the metadata, the Flink execution engine, and then Pulsar for the read and write data in and out of that session. So why would we want to use Flink versus the Presto Pulsar SQL interface, right? So one is it can perform queries and inserts against Pulsar topics. Presto SQL cannot do inserts. It can only query the data. You can get the JSON back, and then you'd have to take that JSON and then redo it, but it's not a native, right? You can't say create table as select, or do a select insert into operation with Presto. SQL with Flink, you can do that. You can do streaming analytics and run continuous running SQL queries, right? So you could with Flink, you can say, I want this process to stay running, and as new data comes in on these topics, to spit out the new records as well. Whereas with the Presto one, it's a static point in time query, right? It goes and reads against the segments in BookKeeper, which is static data. It'll read all the data that comes into those segments, but once that segment closes, that's it. There's no more data coming in after that point. Where with a Flink continuous running query, you could leave that thing running for 4 days. As data comes in, as it rolls over segments and ledgers, it'll just continue to process that data against it as well without any sort of issues. And yeah, so this is a way to join. And so that's the bullet point 4 here is, right, you can query both historical and incoming topic data. Whereas with the Presto SQL, you're doing mostly historical and incoming up to the point of that last open segment. So again, if that last segment is open, it'll fill up, but that's it, because the way that the Presto query engine works is it says, okay, I want to query this data. Where's the topic data? It gets the list of segments at that point in time and then queries them. And that's it. It does not go back and say, are there new segments or new queries for me to go back and read again? So incoming topic data no longer gets read with the Trino Pulsar SQL connector, whereas with Flink, it continues to do that. And just like the Presto SQL, you can join data from multiple topics and streams together, which is a great use case that, for multiple different use cases, but you cannot do this with Pulsar Functions, for example. So that's, again, the limitation where Pulsar Functions cannot do this. You can do, content-based routing. You can do filtering. You can do all sorts of cool operations on streaming data and ETL pipeline type operations with Pulsar Functions, but you can't do it across multiple streams. Flink SQL solves that problem. So if people need to do something across joining multiple tables, then we need to refer them to Flink SQL, and they need to use that to provide those capabilities to them. Let's talk a little bit about the abstractions in Flink relative to what we saw with Presto SQL, right? So again, a catalog in Flink is just a collection of databases, and this maps to a Pulsar cluster. So entire Pulsar cluster is considered a catalog in Flink speak. A database is just a collection of tables, and it's mapped to a namespace. So again, a database is a namespace in Pulsar. All the different topics of the individual tables as shown here. So each Pulsar topic can be presented as a streaming table or an upsert table. And we'll talk about this in a little bit, the differences, between those two. And then last but not least, obviously the schema is the schema associated with a Pulsar topic. And it's mapped, again, we go and you query the metadata store, the schema registry in Pulsar to get this information, the name of the fields, the types of the fields, the nullability of the fields, defaults, etc., whatever sort of semantics you have on the schema, that is also accessible, and Flink needs to get that information as well. Now, as I mentioned before, you can map a Pulsar topic to a streaming table or an upsert table. So streaming tables in Flink are immutable. They represent unchangeable facts. From a Pulsar topic perspective, these topics are append only, and new data can be inserted, but existing records cannot be changed. So by default, all Pulsar topics are mapped to streaming tables in Flink SQL. They can also, as mentioned here, they can be created or deleted via DDL queries, where the underlying Pulsar topics can be created or deleted. So streaming tables are the default, and they're immutable. You also have the option of mapping a Pulsar topic to an upsert table. And upsert tables are mutable. So they are more like traditional database tables because they support create, read, update, and delete operations. Currently we cannot use Pulsar table in upsert mode at this point in time that I'm aware of, but that might change in the future. But you can do an upsert into, so you want to select from a streaming table, you can put it into an upsert table, mutate it, and then write it back into a Pulsar topic to update that. So if you wanted to bypass this restriction for now, that's kind of one workaround, is to read it as a streaming table, map it to an upsert, write all the data there, do some filtering on that, and then manipulate it, and then dump that resulting upsert table results back out into Pulsar as well. And again, they can be specified by to be an upsert Pulsar. So these are net new tables as well, and they can be created using the Pulsar Flink connector for this. But basically, if you want to execute an interactive Flink SQL queries, you'd have to bring up obviously the command prompt. Then you select the Flink cluster in the Flink catalog, which would be the Pulsar cluster you want to query from. Select the database name, and then on the right side of the SQL editor page, again, this is all related to when we had StreamNative interactive. There was a shell that would do this. They'd give you a catalog, you'd select on it, run these queries. This is no longer something that we support for StreamNative as well, but there was a way to execute this, so you have to replicate this behavior using the Flink provider's interface that's provided to you, right? So this was something we used to be able to do for StreamNative. We no longer offer this for our clients. This is an example of how we can load data. You can create a Flink cluster. You can run this on another Flink cluster. You don't need to use ours anymore, but there's a guide for how to do this information, right? And there's commands that quickly walk you through the process of, once you've downloaded, you've cloned this repo, you go into the taxi data and you run these commands, and you can, upload the data there. This is, again, was using the StreamNative interface for this, where we would connect to the Pulsar instance name. We'd use the OAuth 2 authentication. We'd give it the broker service URL, and you can basically load up this information, right? So it would say, this tool would basically load a set of predefined data into two different topics, green taxi, yellow taxi, using this interface. It's designed for that. I'm sure it works, but you're just going to have a different, authentication credentials to, or this is to read this information from and get it out from Pulsar. But I'm not sure where it's going to write this. So this is going to load the data into two Pulsar topics, and then you can run the queries on that, right? So this is there's very detailed README instructions on this, but it's basically can help you load this data and run some queries against it, so you can test Flink SQL there as well. So, just to summarize, it's a useful tool for answering questions about data, getting real-time analytics, anomaly detections, data pipelines, and similar use cases. It's intended for high throughput queries and for running continuous queries that update as new records come in. So it is very similar when to use it. Again, the big distinction being I want to run continuous queries versus I want static point in time queries. More or less the capabilities are the same. The Flink SQL context is the same. You just have to configure the Flink connectors or the Pulsar Flink connectors in order to access that information as well. So now that we have set up between, what the Presto SQL is and Flink SQL, let's dig in a little bit about basic Flink SQL and some of the more complex commands you can use using Flink SQL to create tables, insert data, do querying, filtering, and aggregates on that, if Flink is your execution engine of choice. So Flink operates against logical tables, just like a traditional database or any other database. And the table consists of logical schema that defines the columns and the types in the table. And this is what the queries operate against, right? So you can define a brand new table or map an existing Pulsar topic to a database table in Flink, either way. But this is an example of how to create a brand new table. Let's say I want to create this particular table here. This is your basic create table syntax, very similar to what you do in a traditional database. Nothing super fancy there, but you can do also do create table as select, which is, so you can select from one table and insert it into another, do some filtering down some fields and things like that are all options available for you. As well. Again, this is one that's not backed by Pulsar. Now, if you want to create a table on an existing topic, this is the syntax to do it, right? So again, you are explicitly specifying what you want the fields to be. And in the with stanza here, this is where you specify all your different connection details. I'm using Pulsar. What topic does this table map to? What's my key? I have a key field in that record. What does that map to? What's the value format? They're Avro records. Where's the Pulsar broker? Where's the admin URL to go get the information? And where do I start reading this information from the latest, the earliest record in that topic? That allows you to control that as well. So this is how to create existing topic against a Pulsar, table against a Pulsar topic. If you create a non-Pulsar back table, so again, this is back from the previous slide, not this one, then you can insert records into the table just like a traditional one. So we cannot insert into Pulsar topic back tables, but you can do regular inserts into a non-Pulsar back table. And the syntax is exactly the same. This is just doing multiple inserts. Just like this, you can do that sort of syntax here to update that information, start putting data into that particular table. And then you can query against it at a future point in time. You can also, as I mentioned, kind of alluded to earlier, you can also use the results of a select statement to create and populate an entirely new table, often called create table as select or CTAS syntax. It's a common approach. You first create a table like this is what I want. These are the fields I'm interested in. Then you do insert into that table you just created and selecting specific fields from another table. This could also be a Pulsar back table or a non-Pulsar back table. It does not matter. But this is one way to sort of bring that data in. So again, if you want to pre-filter some data, knock out some fields, do some analytics on it, this is one great approach to do that, right? I want to grab data from a Pulsar topic, so coming in, filter out the fields, and then do some upserts into it, and then maybe take that information and do something with it, output it to another topic, another table, or another system. That's something you can obviously do, and this is one approach to doing it. As would be expected, Flink supports standard where statements for filtering data, as well. And, from this point forward, just note that all these features that I'm going to talk about, this slide forward, work exactly the same regardless of whether the topic is backed by Pulsar or if it's not backed by Pulsar, right? So you can everything you can do here, you can do against all types of tables, right? So you can, do a filter, you can do a where from, price, things like that. Again, if you want to specify, this is showing you can always pass through startup options. If it's a Pulsar table to say when I want to start scanning the data from, that's an option you can always pass it here. We're here or not. We've commented out, but I just left it there, right? So you can do standard filtering, no problem. This is, again, we've alluded to it. You can add that scan startup mode configuration property to specify where your SQL queries will start in the Pulsar topic. There's a couple of defaults. Obviously, earliest is there. Latest is a enumeration. It's the latest, and it maps to the most recent data. It skips all the older historical one. Third option is you can tie it to an external subscription, right? So if you were reading it using another subscription for whatever reason, you want to store this information and retain it for historical reasons. Say, hey, I want to pick up where I left off. For this, then you need to specify this particular parameter here. Say, hey, use this particular subscription name, and that will be kept and retained inside Pulsar itself, which is kind of a cool advantage. So if it ever dies and you want to pick up where you left off, but not reprocess data, not process duplicates, then using an external subscription to mark your place and your position is a great alternative as well. So this guarantees that you don't reprocess that data. And if you're really adventurous, you can also specify an exact offset of where you want to be, or user specified offsets. And again, the parameter is specified as a message ID, which is this tuple of data information where all offsets all ledgers are kept, right? So ledger ID, an entry ID within the ledger, and then potentially a partition ID as well within that, right? So this is an example here. You'd have to explicitly record this information to have something that is of any meaning to you. But nonetheless, this is an option where if you're recording a particular offset, let's say you're doing a reader interface in your application, and you know where you left off, and you're doing your traditional checkpoints, and you're storing that in a third-party system, and it dies, you go back and read these offsets from wherever you stored that information, and then you can start exactly where you left off as well. So this is a way to guarantee exactly once processing using the reader interface versus using a subscription model for that. Also, you can support aggregations, right? So again, this is something that, everything you can do, counts, averages, mins, max, are there group bys as well. This is the syntax for that. So you can do sum of price, grouping by product ID, for example, on the streaming table, it produces an updated result. So you see, if you do a streaming table and you do continuously updating, then the aggregate price is going to change, right? You'll see. So this would show you the total amount of sales for a particular product ID throughout the day until you stopped it, right? This would just be a continuously updating query, for example. You can create temporary views, so you can break them into, your these large complex queries into much smaller reusable chunks using temporary views, and you can, define it as this, create view as this. So you're doing a, order 3, and then they can be reused in another query or script. So you can start piecing it together, making it more logical. It's something you can do. It's a logical view. It's kept in the metadata store for Flink, and it's just retained, and you can use it again in future queries as well. So let's move into more advanced Flink SQL. So we saw the basics, right? So this is where Flink starts to differentiate itself versus the Presto Trino engine to some extent. We're going to talk about the more advanced capabilities of Flink SQL, to do some real-time analytics. Windowing queries are based on times, which are kind of interesting. A lot of people for analytics want windowing, and then obviously joins from different streams are some of the more advanced Flink SQL commands here, right? So let's talk about, tumbling windows, right? Tumble is a built-in function for Flink SQL that does this grouping and batching for you automatically. It groups things based on timestamps within Windows. So unlike other aggregations, only produces a single result versus like a continuous query. We're doing the aggregates. We're always updating the product ID. This is going to be calculate one exact result for each window here, right? So this is basically, doing a process time of every 30 seconds. The process time is a field within this particular table here from the orders table. And you're saying every 30 seconds, I want to create, that's my windowing interval, and I want to sum of all the prices by product ID, right? So you're grouping by product ID. It's going to give you the value of all the sales by product ID over that 30-second window. This is what this particular query does. And that's all you have to do to set up that particular window. And this is it. The group by tumbling handles that for you automatically. And the Flink execution engine knows how to do that. So it's a really cool technique that's there that the things like, I'm not sure Presto SQL has, for example. Another cool feature that Flink SQL provides is the watermark here example. So you can record in all records within 30 seconds earlier than the order time are expected to be ready. Sometimes you'll have late arriving data, right? So records that occurred within one particular time window, but due to delays, they don't arrive until after the time window has closed. Let's say the previous example, right? We're trying to do those 30-second windows, but something that should have fit in there because the process time didn't because it was arrived late. So to account for this, you can use the watermark function to specify how long you're willing to wait for late arriving data to show up, right? So this example shows how to use the watermark to work with timestamps and records, and all the records with 30 seconds earlier than the order time are expected to be ready. So you're saying I'm basically doing the same windowing as I did before, but I'm also adding this tumble row time is basically saying this is my high water mark. I want this to be, I'll wait up to 30 seconds for late arriving data, and it won't skew my results as well. So this is, again, another feature that's native to Flink SQL. It's not available in other query engines necessarily. Now, this is one good example. We talked about one of these cases was like, mobile applications, web applications, monitoring, filtering, things like that. So if you wanted to count the number of orders per user for a session, you can use the session built-in group windowing function that comes with Flink. And so in this particular example, a session is bounded by an interval of 10 seconds. This means that orders that occur within 10 seconds of the last seen order for each user are merged into the same session window, and any order that occurs outside of this interval triggers the creation of a new session window here, right? So this is just something where you can sort of predefine how big your sessions be, and if something occurs within that window, then you consider it part of the same session. Another good example would be web clicks, right? You're monitoring web clicks from people. I'm sitting on a website for a little bit. If I click within the next 30 seconds, that would be, you group it into logically in the same user session. If I went away for longer than that and I came back, then you might break that into a second session, right? So it's a way for you to predefine how long you want, or how big you want what you consider your session windows to be when you're dealing with time series data. This happened, and this happened, and this happened. What considers it part of the same session or not is obviously controlled with this these built-in features here as well. Another cool feature that's provided by Flink SQL is the rolling aggregations using the over command. So in contrast to the group by aggregates, the over aggregates do not reduce the number of result rows into a single row for every group. Instead, the over aggregates produce an aggregated value for every input row, right? So this example tries to calculate the total price based on the processing time and the product IDs. So we will compute the total number sold, count, and the total price sum for each product over the specified window, right? And so this is a way to do that sort of thing. So rather than having do it into one and run multiple queries that do it for each individual group by, you do the over aggregate and you get basically a group by semantics, but you have multiple results for this as well. So it's another cool feature that's there. You can also specify windowing as this, which this example shows. So you can window by process time as well. And window all the rows between this one and that one, the last two, the last five, whatever. All these are available here. So you can do rolling aggregations quite easily using Flink SQL. And this is something that would be useful for, again, real-time aggregates. I want to do a sum across all sales in my e-commerce site. I want to for all the products. This is a great way to do it with very simple syntax as well. If you need to calculate the top n number of records for some aggregate value, then the following technique will do the trick for you very easily. In this example, we're calculating the top selling products across all orders. So if product ID 5 has been on 100 different orders, then it will currently have a count of 100. And that would be the highest selling order by count, right? So this is, basically saying this row number over by the number of orders, and then you're just doing this count. And so you're saying, and then give me the top 10 or the top n of those as well. And since Flink SQL supports continuously running SQL queries, these product counts are continuously updated, and the order count for product ID will increase or decrease. It'll change based on these windows as well. And so you can sort of see what your hot products are over the course of the day and trends throughout the course of the day. And this is, again, built in to the system, and it's built right there inside of the Flink SQL. So it's another cool tool to have. If you have a topic that might contain duplicate data, then you can use this following technique to identify and filter out duplicate data. So in this example, we're using Flink's built-in row number function to auto-generate a unique row ID for each row in a result set. This way, if there are any orders with the exact same order UID and order time, which is a good indication of a duplicate record, then these identical rows can be distinguished by these auto-generated row IDs. And since we only select the first row, where here at the bottom where row number equals 1, then we automatically filter out any and all duplicates, right? So you're basically tagging this row number. If you have any unique ones or duplicates, you can account for that with SQL queries for whatever reason. So again, if they didn't use the right semantics to put the data in a Pulsar topic, or for some reason they didn't use a transaction and there might be duplicate data in here, you can account for that at query time using this technique as well, which is a nice tool to have in your pocket when you're doing analytics on it, and your results have to be exactly right. Last but certainly not least, Flink SQL supports complex and flexible join operations over continuous tables. There are several different types of joins to account for the wide variety of semantics that your queries may require. Flink SQL supports all the standard join semantics that normal databases provide. As shown here, inner, outer, left, full, right joins, and all combinations thereof, and they act exactly as you would expect on anything else, right? So you can join orders to product, joining onto key fields being the same, and et cetera. That works as you would expect. You can also do interval joins, right? So an interval join is defined as by a join predicate that checks if the time attributes of the input events are within the certain time constraints. The interval join is more useful to keep resource utilization from going, indefinitely. So you sort of drop these orders every often, continuously build the information into memory and exhaust your memory heap in Flink. So this example here, the SQL here shows how to join events of two tables, the order simple and the ship table, that correlate to each other. To reduce the number of input rows, Flink has to retain and optimize the join operation, and you can define a time constraint in the where clause, right, to bound the time on both sides to that specific interval using a between predicate, right? So rather than join everything, you're only interested in all the orders, records from the order table and the ship table that are within the 3-day interval of one another, right? So you're saying, hey, this data, don't join all the data forever, just scan it and limit it to the past 3 days. So you can do an interval join as well. And this natively does your where clauses and in-betweens for you automatically. This is, again, another benefit, advantage that Flink SQL has that's cool for using and analyzing real-time streaming data, which is our use case as well. So I thought I'd bring these to light. Moving ahead, let's talk about the StreamNative SQL, is what we call it for now, for lack of a better term. But understanding how the StreamNative SQL architecture works, it's called the filtering and routing service, is what I called it earlier. It provides a way you can use SQL query syntax to pass into the filtering and routing services to do broker-side filtering of messages and route messages from an input topic to an output topic using SQL syntax and avoiding the cost of having to send the data across the wire to the consumers who are just going to ignore it anyways. So this is kind of what it was designed for. All right, so why do we decide to build, or what is it first before we get into it? So again, it's a SQL syntax-based service for filtering and routing data on the broker side. Supports write operations to create new data by routing it from one topic to one or more output topics. And under the covers, it uses Pulsar Functions to implement the SQL query logic. Just as a limitation, it only works on new messages. It does not go back and query any historical data. So that, again, that's a limitation of that. If you need to do historical data queries and move it from point A to point B, you got to look at the Flink SQL or the Presto SQL interfaces that we talked about earlier. This is only on net new messages. And Similar to Flink SQL, it also these queries run continuously until you stop them. And so it's just, again, it's just a continuous filtering operation done on the side inside the Pulsar brokers. So this is the design diagram of what the SQL gateway contains. It has a REST server and a runtime engine. This gateway is similar to what the Presto and the Flink SQL gateways are. It's just an interface that the user can send SQL syntax to, and it can do it has a subset of APIs for managing the queries, running queries, getting status, health checks, things like that. You submit the query to it, and then it decides to, right now it's a pluggable runtime interface. There's just one available, which is the Pulsar function. Later on, it can expand, have other runtime interfaces, but it translates the SQL syntax as any other query engine into a abstract syntax tree, and then a query execution plan. And this is executed using Pulsar Functions there, and then these external computing engines, which again is this case Pulsar Functions only, executes the query and is going to and return the results. So it is, essentially a REST server that allows users and applications to submit and run SQL queries on Pulsar Functions. Underneath the covers, it's parsing by this StreamNative SQL parser, and the gateway, again, traverses the abstract syntax tree, maps it to an execution plan in the runtime environment, and they can be configured again and used as separate libraries. Right now, only one is supported. In the future, we can add additional ones as well. So you map it out to your individual runtime package. It's compiled and built up to be your set of Pulsar functions, and load the packages and starts them running. Currently, Pulsar Functions is the only one supported, and you can query and run this information, get all this information through the admin API, start it, stop it, check on the status of these things, manage them, things like that are also all provided as part of that REST API. As we saw in the previous slide, you have a subset of commands that you're able to do, check on the status of it, run it, things like that. To make it simple, this was a design choice. You're going to have a serverless way to build up this StreamNative SQL based on the Pulsar functions here. And so again, the user submits something to the SQL gateway. He's going to maps those commands over using Pulsar client, Pulsar admin client, submits it to the Pulsar cluster and creates these different functions. Parser functions, there's a routing function running in real time. These are continuously running functions that are the core of the Pulsar function runtime environment. So this is what does the execution of the logic. These SQL queries eventually get mapped and passed first to the parser, then to the router, and then obviously to the runtime functions. And they're divided up into different separate functions so they can scale independently as well. There's not one big monolith that's going to crash and bring everything down. So what type of things can you do with the StreamNative SQL? Right, so you can obviously do a query on this and redirect messages to standard output if you just want to do a query and do an exploratory analysis and say, hey, I want to look at the data that's coming into my topic, right? I don't want to do anything with it. I just want to peek at it and see, for example, from this input topic, am I getting anything with these particular keys? Yes or no, or you can do a count on that or something like that. You can do some additional things, just do some analytics. So just basic queries, but not do anything with them. Just read the data, look at it, see what's going on. Again, you can do redirects, right? So you can do filtering, and then, like we saw in the previous example, create table as select. This is a similar concept, right? We're explicitly selecting from an input topic, and those values that map these particular fields are then being written to a separate output topic. So this is a redirect. You're able to actually create topics on the fly, populate topics on the fly, and do content-based routing directly again on the broker, rather than send them down to a Pulsar function to filter them out, or to a client and that ignores them. So it's a more efficient way of doing it. And this can be obviously easily expressed as a SQL operation as well. Again, you can do a fan out, right? So you can route incoming messages into one of multiple output topics based on their content. So this is, again, if I have a particular key value mapping to a different values, I can route them to different output topics as well, and then have a catch-all from there, right? So you can do all these different ways. You can do a fan out, you can do a fan in sort of thing, but the insert multi is the syntax required for that. That's the key takeaway here, the insert multi, and then a sequence of if else, if then else statements as well. And then obviously the source where you're getting the information from as well. So again, this is a fan out operation is supported. So when would you want to use this? When you want to do basic filtering, routing of messages from one topic to another, and you don't need to use a complex processing engine to do that. Obviously, it's doable with Flink. You could do it with the Presto SQL as well. You dump it out to JSON, route it back in as well. But if you want it to be much more simpler and easier, this is a great use case for that. If you want to pre-sort your data on a topic to minimize the amount of data sent from the broker, this is another key use case, right? If you know your downstream consumer is only interested in events with this particular serial ID or key ID, and 90% of the data you're going to send to it is ignored, rather than wasting all that bandwidth and resources, just do this and route them into another topic and then have them consume off of that topic and save yourself the bandwidth of sending it down only to be dropped at the far end, right? So again, these are just some examples of this, content-based routing, real-time ETL pipelines, sorting and filtering good messages, bad messages. You can sort of filter them through, as well as just some examples of that. You could do many other things. The sky's kind of the limit on that. Just say thank you. Hopefully you found it educational.